Okay guys, so this question here is question 10 on 10C. A particle moving in a straight line such that its distance x from a fixed point at time is given is x equals r cos omega t. Show that the particles move in similar magnetic motion. Do you want me to do one more of these, or are you very happy that you can differentiate twice and show that's in the opposite direction? One more. Okay. So one more. X is the displacement is r cos omega t. The first derivative is the velocity. Differentiate once. R is a constant, it stays on its own. The differentiable part is the cos omega t. Cos changes directly into minus sine omega t. The angle remains unchanged. Then you actually have to look at the angle and differentiate the angle with respect to t. If that was cos 3t, when you differentiate the angle, the answer would be 3. This is cos omega t. So when you differentiate the angle omega t with respect to t, it's whatever letter comes in front of the t. So the answer would be omega. So that's where the extra omega will come from. So you're going to have omega here, and then you're going to have minus rw sine omega t. That alright? Second derivative, guys. Second derivative. d2x dt squared. Differentiate it a second time. Minus rw. What does this change into? Anybody? When you differentiate it? Cos. Angle remains unchanged. Differentiate the angle. What happens then? Omega. Minus r omega squared cos omega t. Compared to the beginning, if you look at x, x has r, cos and omega t in it. So r cos omega t. So what you get here, guys? Minus omega squared x. The second derivative is the acceleration. Acceleration equals minus omega squared x. It's executing simple harmonic motion because the acceleration is directly proportional to the displacement x, and it takes place always in the opposite direction because of the minus sign. That's why it's deemed to be doing simple harmonic motion. Any questions on that? I'll stop it there. Your acceleration is proportional to your displacement x, and it always takes place in the opposite direction, hence simple harmonic motion. Now, a particle is moving in a straight line with simple harmonic motion when it is at a point P1, 0.8 meters from the mean center. The mean center means basically the place where there's no force. Okay? So if you draw your diagram, this is the equilibrium point, or the mean center. Okay? It says it's a positive distance of 0.8. So x equals 0.8. So this point here, let's call this 0.8. Okay? So when x equals 0.8, your phi value is, anybody? Your phi value is 6. There's a second point when you are at point P2, a distance 0.2 meters away from the end position on the same side. Now this is an interesting one. End position on the same side. If you take that the distance from your maximum value, you know when phi equals 0, yeah? If we take that distance as r, that from the top to the the biggest distance away from the center, where your speed eventually turns into 0 and you start to reverse directions, if we take that value as r, what we're then told is that this position P2, so that's P1, but we're told that P2 just happens just before this. In fact, 0.2 of a meter before this point. Please remember that x is always the distance away from the, anybody remember? The center. X is always the distance away from the center. This makes our x value r minus 0.2. And our phi value would therefore be equal to, what's our phi value then? It doesn't give us a p value, it gives us an a value. It gives us an a value of 24. So When you assemble this information, the next part is all about choosing what formula to use. We write down a few of the generics. Phi squared equals omega squared alpha squared minus x squared. We can also have, what's the acceleration one, guys? Anybody remember? Acceleration equals minus omega squared x. We can now use the two of these, and we want to prove this ratio here. So here's what we're going to do. We're going to say that phi squared, we're going to use the first one, phi squared is 36. Omega squared we don't know. Do we even know the a value? We don't. We're going to have to keep it as r. Do we know the x value? The x value is 0.8. Okay? That's one equation. What about the next equation involving this one here? What's the a value? 24. Omega squared, we don't know. Minus omega squared, we don't know. Excuse me. Okay. What's the x value? R minus 0.2. Now, what I'm going to do next is I'm going to divide one by the other. So I'm going to do this, and we've seen this trick a couple of times already. So what happens now? 36 divided by 24. 3 over 2. Omega squared divided by omega squared cancels. I'm going to multiply the bottom by minus 1. So I'm going to get 0.2 minus r. And now I'm going to get r squared minus 0.64. Does that make sense? 0.8 squared is 0.64. Then I'm going to turn both sides upside down. Did I make a minus 1 mistake? Here was, I was told that initially I took x as 0.8, didn't I? A positive 0.8, correct? And therefore this displacement here, whatever its value, is also a positive displacement, because if you read the language of the question, it says the same side of the mean center. So it means that all the action is taking place to the right hand side of the center, where x is in the positive region. Remember what we always said about simple harmonic motion? When x is positive, a must be negative. It says of magnitude 24. That doesn't mean it's 24. It means it's of magnitude 24. I really should have put down a equals minus 24, because the acceleration has to be driving it back to the left, decelerating it. So what would have happened here was that would be a minus 24. Now that I do that, what happens is it's r squared minus 0.64. And see the minus. The minuses cancel each other on the bottom. See that there's a minus on both fractions. They just cancel each other out there. And now you're going to get r minus 0.2 equals that. Turn them both upside down to get 2 over 3 equals r minus 0.2 all over r squared minus 0.64. Okay,